Hello, PreCalc. You're observing this on Tuesday after Tuesday's class, so that's 1-3-17. It'll be all theory, and I'm going to go through it rather quickly, so I will reduce the video uploading time, but you can pause at any point to write it out if I get too far ahead of you. Everything is theory today, so I won't have a chance to show you any problems. But I think now that we're halfway through, basically almost halfway through our pre-calc year, you should be able to observe mathematical theory and apply it to problems. So I'm going to be expecting you to do that with this topic. I'll tell you what the topic is in just a minute, and part of it will come from observing these two lists. Those who've had physics recently or having it now will be an advantage. Notice these quantities and these quantities separated by this line. What separates these two quantities? Well, these have two aspects attached to each one. These have only one single number. So time is one single number, and like 3 hours. Mass is one single number, like 3 kilograms, whereas displacement, velocity, acceleration, and force have more than just a number. What's that other thing that this list has that this one does not? I hear it through the video. It is displacement, it is direction. So direction. So it's more than a single number over here, and that is called a vector quantity. Those are vectors over here. These are not vectors. Do you recall what they are? Scalars, scalar quantities. So over here I'll put in the theory that we're learning is vectors. All right, some will repeat from those in physics class. All right, so when you have the magnitude, which is what I call a number part, the magnitude and direction, then you have a vector quantity. Vectors have both. All right, and we're going to represent vectors. They're going to be represented by a directed line segment. And recall from geometry class what those are? A directed line segment? It is a ray. So a ray, you'll recall, can be drawn like this. It starts at one point and it goes in a given direction. So it's indicated by a starting point and an arrowhead. That is a ray. And I'm going to call this ray, I'm going to call the point it started with R, the initial point, and the point where the arrowhead ended is S, and that's the terminal point. I can name this vector two ways. I can call it RS with the vector symbol over top, or I can sometimes just call it usually a lowercase emboldened. It's hard to write emboldened, but in your textbook it is better, more obvious. So this vector V is another way we can name a vector, so you'll be using both. All right, let's look at two vectors at once, if I'm not asking too much. Here we have vector RS, and here we have vector PQ. My point about vectors at this point in our discussion is vectors can be moved all around. So I can pick up this vector and move it over here if I want, or move it over here. As long as I keep the direction and the angle true, I can move vectors around. If I pick this vector up and move it on top of this vector, and it coincides exactly, and it has the same length and the same angle, then we say that those two vectors are equal. So I can say vector RS equals vector PQ if the magnitude, that's going to be the length or number represented by this distance, and the direction is the same. So I can say that vectors are equal. All right. Let's talking about moving vectors, let's take this vector right here and let's just move it so that its initial point, R, is at the origin. So where should it go? Where it stops, nobody knows. Bing, bing. All right, so that's what I did down here. I picked the vector up, kept the magnitude and the direction true, and I moved it so the initial point is at the origin and set the vector up like this. When that is done, it's called standard position. All right, again, this is review for many of you, but I'm going nice and slow and making it clear for those who have not seen this. All right, let's look at a vector, an important part about vectors, and see if I can get a clarity there. Here are two vectors, and I am interested in expressing both of these vectors in what's called component form. So any vector any vector can be divided into two parts, an x component and a y component. So notice I went from the initial point to the terminal point, but I went in a horizontal step and then a vertical step. So these are called components. This is the x component, this is the y component. Any vector will have them here. This is the x component, this is the y component. And it doesn't have to go in that direction. Let's take a vector that starts here and goes this way. This one has an x component. Notice it went backwards. It would have a negative x component and then a positive y component. So notice any vector can be divided into horizontal x components and vertical y components. When we do that, we can list them, the components, instead of in parentheses, to tell the reader that we're talking about components. We can say that we use these pointy parentheses, and we go the x component and then the y component. So as soon as you see the pointy parentheses, then you know that we're talking about the components. So vector v, in theory, if we have a vector v, that's my emboldened v, its components are v1, comma, v2 in the pointy parentheses. This way of writing component form is very common, and I want you to recognize it. And this is the x part, this is the y part. So when a vector is in standard form, we talked about that, it's when its initial point is at the origin. Here's what the x component would look like, and this is what the y component would look like. All right, so when I give you a problem, which I'm not going to do in its entirety, I'm going to give you components like this. So if that's a vector, it tells you that the x component is 2 and the y component is -4. So if you were going to draw it in standard form, you know the x component went over 2 and the y component went down 4. So the vector went like this, over 2, down 4. But it doesn't have to be in standard form to have these components. It's easier to visualize it, but that vector could be, same vector could be, let's put it up here. Do you see how this vector also has these components? You go down 4 and over 2. So the negative y component of 4 and the positive x component of 2 represented by these numbers. All right, so when it's not in standard form, we're going to give you a little formula which should make sense. So I'll start with setting up the problem. Suppose I have a vector PQ. It starts here. The initial point is P1, P2, comma P2. So that's where it starts on the coordinate plane. So if I go over P1 and up P2, I can get to this point. So over P1, up P2, and that is indicated by the name on the coordinate plane, P1, comma P2. This is not component form, this is parentheses, it's just the name of that point. This point is Q1, so I went over Q1 and up Q2 to get to this point. Its position on the coordinate plane is Q1, comma Q2. All right, so let me remove this so it's not so cluttered. All right. So I think everyone knows this is the X, that's the Y to get to here. This is the X, this is the Y to get to there. All right, so we're going from point P to point Q, and I am going to also call this vector V. So its components are V1, V2. So recall that means the components are this. There's my V1. My X part, and V2 is my Y part. So how can I get those? Well, in theory, if I know that the X coordinate of this point and the X coordinate of this point, to get this value, I'm going to subtract this X coordinate from this X coordinate. Study that, and that should make perfect sense. So the Y part, how do I get V2? I'm going to take the Y coordinate from this and subtract from it the Y coordinate from that, and it'll give me this part. So the X component is Q1 minus P1 in this picture, and the Y component, V2, is Q2 minus P2. Actually, these problems are easier to do in real life than they are to talk about in theory. So, as I said, I'm not going to do one in its entirety, but say we were at 1, 2, and we went out here to, say, 1, 2, 3, 4, 5. Say we went 4, 5. How could we get the X component, or V1, and the Y component, which we also call V2? So if this is vector V, the X component now recognized as V1, and the Y component we're now recognized as V2. How would we get this value, this length, and how would we get this? Would we not subtract the X values 4 minus 1 to get this, and the Y values 5 minus 2 to get this? All right, that's just a hint of what a practical problem would look like. So, to finish our discussion on this, I also need to know how to find this length right here. So I found that this side, V2, was Q2 minus P2, and this length here was, V1 is going to be Q1 minus P1. So we already established that here. I just put it on the picture. So how could I get this length if I know this value on this side of the triangle and this value on this side of the triangle? Well, it's a right triangle because the X and Y components always meet at a right angle. So we can use the Pythagorean theorem. We indicate the length of vector V with double lines like this. So this means the vector's magnitude. 2 lines here and 2 lines there. That all that means is the length of the vector, the magnitude. And we do that by taking the square root of this side plus this side. Doesn't matter which one's first. I'll do the 2's, Q2 minus P2, and then the X's, Q1 minus P1. Oops. All right, so this is using the Pythagorean theorem, we get the magnitude. All right.